Right, we shall go. Who works in financial services here? There's a few of you. What else? Telcos? What other businesses or industries do you work in? Who lives in London? English? So where else are you guys from? Germany? France? France? Switzerland? Okay, so all of you guys that haven't said anything, tell me where you work and where you come from. Oh.
Outside London.
Oh yes, is there something outside London? Sorry. Okay. Okay, well, I'm going to go through, actually this thing might work, this might be quite cool. Now I can walk around a little bit more. So I'm going to go, this is sort of rather strange timing for me, as I'll explain on the next slide. This is a talk I've done a few times. It's a technology piece of software which I've been working on for a number of years, sort of spun off in different directions. We've done different things with it. I wanted to create an open source version of it as well, but for the moment we kept a version of this. So what I'm going to give you is all the secrets and sort of tell you exactly how it works. It will make a massive difference to your data. I'm presuming you all work in Java here. Yep, good, that's reassuring. And some very, very simple things you can do that will make not just a massive difference, but an incredible difference. We're talking 2+ orders of magnitude difference to the sort of performance, readability and analyzability of your data. The reason this is strange, because when we have to sign up for these conferences, it's sort of several months ahead, and we put down, okay, could talk about this, could do about that, etc. And of course, I was working for a company called C24, which is still written on my badge. And yesterday, I actually sold the company, or we sold the company, the directors. So all the software that's in this and the talk, etc., this is actually 10th of October, so that went through yesterday morning. And so I had to then get permission to do this talk, because if you like, it's a talk which I wrote when I was in C24, and the acquiring company, Gresham, which is a UK PLC, it's just out of politeness, you need to get permission to sort of redo something that you're doing. So I'm not talking about product, I'm not talking about the C24 product or the Gresham product, but it's stuff which we did use inside. So it's sort of why it's sort of rather weird timing, because I had to sort of move my bio around and change things in bits and pieces. So that's had me busy for the last few weeks, as you can quite imagine. So why do we need to distribute? It may seem fairly obvious to a lot of you. Who uses distributed computing here? A few of you? Okay. Why do we use distributed computing? Well, if you need CPUs, there's only a certain amount of CPUs you can cram into one machine. So of course, you want to sort of move out into other machines. You can scale up inside that single machine, but as we need more computing power, we need to go out. And interestingly, one of the reasons why we need more computing power is because of the laziness that we tend to be with programming, in that the work that we're doing actually needs an awful lot more computing power than it really should do. And what we'll find as we go through this is that we need less and less computing power, and we can actually, although we can still keep the infrastructure that we've got, we don't actually need quite so much. Another reason is memory. One of the main reasons we use memory is that it's fantastically faster than writing to disk or onto the network. Even with SSDs have made a massive change, and there's new varieties of SSDs, and eventually those will sort of combine into sort of the RAM, the memory that we're using, so we will see some of those advantages. But at the moment, we use distribution again to get access to more memory. Sometimes you need compute power, sometimes you need memory, and often both of those together. To give you an idea of this is a classic slide off the internet that you would have probably seen before. The most relevant ones are the ones in the dark, in the middle column here. This is the time roughly in nanoseconds, milliseconds, etc., that it takes to do these various operations. Note that L3 cache access in your average CPU today, not the ARM chips, etc., but your average Intel machine, you've got quite a large L3 cache, typically 32 megs, or sometimes larger than that. That's shared across all of the cores. You've got an L2 cache and an L1 cache. If you can get your data into that, it is incredibly fast. Just look at the difference between the access in the L2 and L3 caches compared with access to ordinary memory. So if you have to go out and fetch a bit of information from memory, so you said search through these, get the information, come back, although your machine is working at umpteen gigahertz, it still has to lock various different parts of the hardware to get access to that memory. And that takes a long time. It's fairly obvious the difference in performance between an SSD or a disk drive and memory, and you can see that, but very few people realize there's a long way you can go further past the memory on this. Gray is just it's not the same as the one on the internet. I just put those sort of to give a little bit more context for people that don't understand or know about microseconds, milliseconds, nanoseconds, picoseconds, etc. I choose a 1 million times multiplier, which is roughly the difference between a modern aircraft and the speed of light, which is 1 million times. The reason that works out is if you're going from, for example, you're going across the States from San Francisco to Tokyo, it takes roughly 5 or 6 hours. Do there and back, it's about 11 hours, so you get the same sort of figures. And it puts it into perspective, the sort of speed that we can get out of this. Now this is important. What I want you to remember is the difference in the L3, L2 caches and the scales of that we get out of that. So moving into distribution, why are we doing this? Well, we've run out of resources on the same on a single machine, and while we've got access to the single machine, things are all nice and work well. These are some of the classic mistakes that we see if we go to an industry that's perhaps doing quite well. It's been around for 20 years. There's an internet industry started perhaps in the 90s, and I see this as a lot because it's the sort of work that I do as a consultant. You go into a company which is now turning over several hundred million, but they've got an architecture that was designed in the mid-90s. So it was designed in the days of Windows for Workgroups, Windows NT. It was designed pre-Java. Java was fledgling in those sort of days. And what they've done is they haven't had the same multi-tier architecture and the scalability that we've had. They didn't have, I mean, they obviously had memory, but they've scaled this thing out based around the database. And I'll give you some examples of that as we go through this. And that's the sort of architectures that we now see and we now need to put into a distributed architecture. What I'm trying to point out here is that just taking the existing number of machines you got, changing an architecture from a multi-tiered architecture, one of the blueprints that we got from Sun, from when it existed, from IBM, etc., and moving that to distributed is something you can do, but you need to think about it a little bit more first, and that's hopefully something I'll leave you with on this. How do we write to scale? Well, it's difficult because you want your processes, you basically want a service-oriented architecture, and yes, we could move into microservices here. So into a microservices architecture would lead us into the ability of having lots of little services around. When we run out of compute power or memory power, we fire up another one of these. We have a naming service so we say we need service X. Service X publishes itself to the naming service. We can now use service X and we can fire up another few of these. So these are one of the ways to scale out. The languages, however, haven't really left us in a very good position to be able to use something which is potentially local or potentially remote. And that makes it quite difficult. You have to think about, you actually have to make choices and changes. And it's one of the things that Java Enterprise Edition tried to do in the early 2000s was to abstract you from the persistence. And we ended up with these awful entity beans, stateful, stateless session beans, and all the sort of abstractions that went around those. However, we do need to abstract ourselves from what's underneath. We want to be able to access a service and for all of that service to know everything about it. So as we come across this, we scale out these things, we do come across a lot of problems. And for anybody that's worked with a sort of distributed machine will suddenly realize that something that runs on your machine with, let's say, 4 cores, 8 cores, or if you've got a server, maybe 20 cores, and then you add another machine, if you're adequately using those and you're using the network between them, you don't actually get linear scalability. It's very much like a cliff. Anything that you've got on here, you fall off this massive cliff of performance because you've got to get all of the information from one machine to the other machine, and you've got to get all the results from that machine back. If not, you've got to distribute all the memory so that all the different processors can work on it. So The problem we're seeing on this, if you benchmark it and you do some micro benchmarks and start looking around it, where is it taking time? It's very rarely the code that you've written. It's typically the serialization and deserialization. Very, very specifically, we tend to use the word serialization to mean serialization and deserialization. It's the process of both ends. But the part which is really expensive is the deserialization. And the reason for this is that the data that has been put on the wire is not in a CPU-friendly format. So when we read data off the wire, it's typically in some format that has to be copied from the network adapter into your CPU memory, and then the CPU then has to decode that because it's in some other format, and then can actually act on it after that. So not only that, but when you read it from your memory card, you've got to bring it into your standard CPU RAM. You have to allocate the space for that as well. And as you allocate more and more space for that, unless you're using ring buffers, you start to fragment the memory, and we end up with garbage collection as well. If we take a look at this, this is from a colleague of mine who's chatting here. This is from the guys at JClarity. This is a nice little sort of post-mortem memory analyzer. It's very useful. It's probably one of the most useful ones. You've got all of these different tools that are built in, but it's very, very useful to see what happened in the past. Now, all this is doing, we can look at the code on this a little bit later, is it's basically just creating a few numbers, a few classes, putting them into so we've got a class which contains another dozen or so other classes. It's serializing them, so it's writing them out to disk, and then it's deserializing them. So the time to create them and serialize them is just this small part here, so 10 seconds. This is doing 5 million of these. So it's writing them out, takes just 10 seconds to write 5 million of these and create them and write them out. But reading them back, the 5 million, it has to create the space for each and every one of those. Create the space, read in the object, create the space, read in the object. Now, naturally, there are more performant ways of doing it. You can do them in batch. But that gives you some idea of the order of magnitude between serialization and deserialization. And that's very, very typical. We take a look at Java and the way it works. And if we really start to understand the way the objects are held within Java and the way that Java treats these objects, we start to understand why this is so inefficient. If we go back to the days of C, C++, anybody here work in C or C++? Good stuff. You'll know what I'm talking about then. Assembler, anything like that? When you get down to these, when you're using these languages, you're working at the metal. You understand the bytes. You have to worry about bit order within the bytes, start bits, stop bits, big Indian, little Indian, etc. And for those of us with grey hair, I can see one other chap, probably younger than me still, but where we were going back into the 70s, 80s, early 90s, you used every single little bit of the memory that you had. We used to use the extra buffers on the video and things for doing bits. And if you wanted to do some processing, occasionally the screen would go all sort of weird because you were using the memory in the screen to do some extra processing. So all these little things. Now, if we want to store 3 letters, A, B, C, it's fairly obvious. I won't bother to ask you the question. How many bytes would you need to store this? Well, typically 4, because you either have a null terminator or you have a byte at the front which says the maximum length of the string. Now, naturally, you could argue that, okay, the string could only be 254 bytes, but that's the way Pascal, it's called Pascal encoding. If we put the null at the end, you can have much bigger strings, but if you want to find out the length of the string, you've then got to go and process all the way through the string to find out where the null is, and that can take some time. So pros and cons on each one. But if you were saying, well, hang on, I'd like to be able to do manipulation of this, I'd like to find the string length, I'd like to be able to do copies. So what's happened is that quite often in the C, C++ world, we built a library around this. We had a string library in some of the sort of later versions of C++. But in Java, there's a library, as you well know, called string, capital S. But every single string is 48 bytes minimum. There's a formula for working that out. So if we put ABC into Java, it is 48 bytes. If you put in hello world ABC, it'll be something like 64 bytes. There's a little formula, you can work it out. It depends very slightly on the Java virtual machine you're using between Java 6, Java 7, Java 8, Java 9, etc. Small optimizations on it, but you can pretty much guarantee 48 bytes. Now, if you copy that and create a second reference to that, Inside that object is a reference counter, and of course the second one will be a reference which will be 16 bytes. However, when your data is coming in off the wire or you're distributing it on a distributed network, you can't analyze it to see whether they're copies, so every single one of those is a new 48-byte string. So if you now have a class which has a dozen strings in it, you've got the class, which is 48 bytes, plus the dozen 48 bytes, so 48 times 12 on top of that as well. And that really starts to explain why we use up an awful lot of memory. It's not just strings, pretty much anything we take. We take doubles with a D, big decimals, dates, array lists, etc. Dates is another particularly impressively large class for what it actually contains. The date has naturally the date, the time, and even down to milliseconds stored in it, but quite frequently if we just want a date, and obviously Java 8's introduced local date, local time, and local date time, so that makes life a little better. But it's still very, very inefficient at storing what we need to know as information. We'll come back to date. So if we wanted to store date, if you were doing this, for those that have programmed in C, C++, you've probably done this, certainly I did in the early days before we had standard template libraries, where you'd use the smallest type that you could find. You had chars, bytes, chars, longs, double longs, and all the different bits and pieces. A year, if you don't need to store the century, for example, you can store it in a byte and a month and a day. And if you did this in Java, you could save a little bit of space. But you're going to have to write a whole class around it, and you'll still get the overhead of the class. In the old C++ days, we could create this using bit fields, and we can actually specify how many bits we need for each of those. Ironically, the sort of rounding up for a date comes to pretty much exactly the same. This is all we'd need just to store the date. So if we compare what we actually need in Java to what we should really need to store this, the zeros and ones there, they're not the real zeros and ones, I just cut and paste, but randomize them a bit. But that gives you some idea, that is 48 bytes in bits, compared with what we actually need, which is the bit in green here. How did I work that out? Well, if you take today's date and time, which I actually did, calculated it for 5 p.m., which is 3 minutes ago. If you take that as the Unix epoch, which is from the 1st of January 1970, that's the number of seconds since then. It's 1,476,201,600 at 5 o'clock today. That's the number of seconds since the 1st of January. And since we don't need the seconds, hours, or minutes, we work out how many seconds in a day, which is 86,400, divide that, and we get 17,085. That, incidentally, is the number of days since the 1st of January 1970. Nice and easy. That number, however, we can store quite easily in 16 bits. And that 16 bits, that is the actual zeros and ones from my binary calculator. And that means that we could store a Unix date in that format. Imagine now, because the processor has read this, we won't go into the efficiencies of 64-bit processors and working with 16-bit integers and things like that. But if we were doing date addition and subtraction, or probably if we're doing big data searching, for example, we need to do greater than or less than, we need to do equals. So we're now searching through an array of dates. So we're trying to get data which is between two dates. It's vastly more efficient for the CPU to compare this than it is to work that out, because the CPU has to basically reconvert and find the information it needs out of that. So each one of those is quite a few steps. What it means is that if we can store the data in a far more efficient format, in the most efficient format so we're not encrypting it, we're basically just storing it in a more efficient format. So again, anyone that's done C or C++ or some of the sort of lower level languages will be quite used to this sort of thing. You don't have classes. So you think, okay, I've got a date. What's the most efficient way I can store it? And that's pretty much what you come up with. So putting this into a sort of little example, let's take some trading data, something you'd be very familiar with, or you'd at least understand even if you're not working in finance. We're buying and selling currencies. So we're buying one currency, selling the other currency. We're doing a swap of the currencies. larger amounts than any of us are unfortunately comfortable with. Well, we'd all be comfortable with it, very comfortable with it, but larger amounts than we're used to, sadly. And we got an exchange rate, so we buy GBP, we sell Japanese yen at 173 yen. This was, I didn't correct the numbers, so it's before the Brexit misery. So these are the pre-Brexit things where the pound was a little bit more interesting. Now, this is very typical of the sort of data that someone sends you. This is the sort of data that you've got to process now. And we'll get back onto serialization for copying this across, because what we do out of this, we'll actually find out that we can solve the serialization as well. Now, if we want to put this, we get it into a comma delimited file. It looks like this. No difference between the two formats. One was in a nice table format for Excel, so you can read it, and one's in CSV. The problem with this is that while you can read it, it's human readable, it's in ASCII. So that 0 is not really 0, it's actually an ASCII 40. So the computer or the processor has now got to, when it's reading a number, it's got to look for the commas, so you've got to look for the commas, look for the next comma, slice that little bit out, and now work out what that number is, and now each time multiply it by 10 as it goes through the digits to work out what the number is, and that's the way the thing works when it's parsing a comma delimited file. If you were to use this, while you'd be able to read it, it's very, very inefficient for the CPU. So what we need to do is to get this into a CPU-efficient format. Now, you could put them into Java. So we put it straight into Java, and I think you'd agree this is a relatively straightforward way that if you had somebody in for an interview question and they said, OK, give me a class for that, and they came out with that, well, they'd certainly move on to the next stage of the interview. I don't think they'd necessarily fail. But what do we get out of this? OK, the long's pretty efficient. And amusingly, some of the work I've done in the telcos, we actually go past the longs, past the end of the longs. We have so many messages, we can actually flip over the counters. We've got a date, so there's 48 bytes. We've got another string, big decimal, double. OK, we end up with precision problems with doubles, so we typically need to use big decimals, but exchange rates are always maximum 5 decimal places, so we can manage with a double. Oh, sorry, 5 significant figures, another string, another big decimal, and a date. So we've got 48, 48, 48, 48, lots and lots and lots of data that's going to be built up with this. Now, you imagine each one of those lines is going to create one of those, and it's going to create an awful lot of memory. That is exactly the data which I showed you on that graph. So the graph is creating, that's easy, writing it out's easy, reading it back in, you're effectively, it's not much worse than parsing the original data. We could, so this is basically just a little bit of code how to parse the line. So in comes the line, we split it on the commas, relatively efficient, gives us back an array of strings, and we can then use those strings to basically call in the setters, and we can set the data. We think everything's fine. Problem with this, every single one of these creates temporary objects, temporary objects are good. They're created in the Eden space, and they're garbage collected very, very quickly. It's the longer term objects that go into the other levels of the JVM, which causes issues. And if we're processing data and we're going to be searching through it, then it's the sort of data we need to keep. So if we do this in classic Java, everything sort of works fine until we start to scale up. Go back to the scenarios I was mentioning of companies which have started in the 90s, perhaps in the early 2000s, nobody could imagine that we'd get into this sort of world of IoT with a completely globalized world where businesses would have literally billions of customers, or hundreds of millions, in the high hundreds, where you've got things like Twitter. If you mention that to somebody in the 90s, it would be unimaginable that you could have that many clients and that much data going through. And so there was no need to design this. But treating 100 million is fairly sort of normal these days in terms of the sort of data you get in. The banks that I deal with are processing high hundreds of thousands per second. They're treating tens of billions per month. So it's the sort of numbers that we're dealing with. So the Java is it's very verbose and it's very slow. While you're sitting on your machine and you're doing something with 1,000 rows or a million rows, it's relatively good. You can run it in a couple of seconds. But when we scale this up, it really causes a lot of problems. This Java actually takes, just to store this in Java, takes 328 bytes per line. The original line is only 70 bytes. So who here thinks that XML is bloated? Right, Java's worse. Java is worse than XML. It's more bloated than XML. So if you put that in XML, it'll actually be smaller. Of course, unless you wrote it in German, which of course it would be 20 times longer. So basically, Java is bloating your data. And this is something that you don't see because the language by design has abstracted you from the whole point of Java was so that you didn't need to understand how the network worked, how the disk worked, how all these different things worked. The whole point of it was to abstract you from all of this sort of stuff. This, to me, is sort of nice, fresh. This is the data that you want to store. This is the data we want to process. This is how it looks to the C++ and assembler programmers. This is the world of Java. Every single bit of information, you remember that 16 bits of data that you had to store a date, which is bloated up to 48, or so 2 bytes, is bloated up to 48 bytes. That's all that stuff is the garbage that is around the Java. This isn't even realistic because in Java, each of these vegetables would be individually wrapped inside the wrapper. So this would be an array of turnips. I think they're turnips, aren't they? You'd have an array of these, but each one of those itself would be wrapped up. Same with these other things. And that, unfortunately, is what we have to. Your CPU spends an awful long time going around collecting that. And just like my son's bedroom, my eldest son, which doesn't look too dissimilar from that, with sort of leftover plates and bits and pieces. If you leave it too long, it just gets to the stage where you can't actually find somewhere to actually sit down and eat. Not that he should be eating in his bedroom, but try telling your kids that. But the problem with the garbage collection is if it gets bigger and bigger and bigger, it takes more and more CPU to actually process it. If you actually take the wrappers off it, you take the garbage off, you put it into if you can do it treat it in the Eden space and basically garbage collect it straight away, it's vastly more efficient. This isn't, however, just a Java problem. So for all of those people that are running around with the latest wonderful language, which just blows everything else out of the water and the world's going to change for everyone, those sort of people, using Kotlin, Scala, Groovy, whatever, Groovy's probably on its way down now. But for people that are working in these languages, it's the same problem. This problem doesn't go away. It's just a different way of programming this. The in-memory caches. Who uses an in-memory cache here? So yeah, and even if you don't use it, you'll probably have sort of implicated an in-memory cache by setting up your own Java list or Java array or key value pairs, etc. Every single one of those, the key is usually an object, or key is always an object. In fact, in most of these implementations, the key is an object, the value is an object. So every time you're putting something in or taking it back, you're doing comparisons, you're doing it with objects. And you're running through these things and they're extremely inefficient. You don't realize it because that processor in this laptop or in your machines is running at 4 gigahertz. It's processing 4 billion instructions, or quite often even more, per second per core. And the reason why it works so fast is because it's getting rid of all of that garbage and unwrapping all of that stuff under the hood. And you've got very complacent, well, we've got complacent with the machines because they just work so fast. The problem is we're not using them efficiently. If you do use them efficiently, you can get at least 100 plus times out of it, as I'll hope to show you. So if we do classic Java binding, that's one way of doing it, but it uses up an awful lot of RAM. We've covered that. We could store the original data. If we did store the original data, we'd have the advantage of the fact we wouldn't need to parse it, so we can put the data in there. It's also smaller. It's now down to 70 bytes as opposed to 324. So we can just basically have an array of rows. The problem is now if we search it, we start searching the data, we have to parse it as we search it. And so searching would be horribly inefficient, unless, of course, you build indices and store up a whole pile of indexes. And then we would have this massive bloat because typically people want to search on everything. And so it also becomes very, very inefficient. It's the problems that you get with storing this. We could store it if we had XML data. I mean, this is nice, simple data, but if you had XML data coming in, it's quite often efficient because the XML takes a long time to parse. It's store it in XML. But again, if you want to search it, you want to analyze it, it's very quick to store, but it's very, very slow to analyze. So I've just been through storing the original is extremely slow. What happens if we compress it? So if we were to gzip, tar gzip, or run whatever zipping algorithm you want to, or compression algorithm on it, yes, you'd use up an awful lot less space, quite significantly less space, probably about a 10th, occasionally a 20th of the space. The problem is exactly the same. You now can't search it because you have to unzip it or decompress it every time you want to search it. However, if we use compaction, compaction is different from compression. If we compress something, we effectively jumble everything up, and everything has to be decompressed to be able to search it. You can compress individual fields, which is one way of doing it, but then the efficiencies of the compression, if you compress A, B, C, you don't get much efficiency out of it. We've got a lot of small bits of data, so the bigger the thing that you compress, the more efficiency you get out of it, but then the more you have to uncompress in order to be able to read it. If we compact it though, what we're actually doing is taking that A, B, C, and we're putting it in if we know enough information about it, we know that that is three letters and always 3 letters, we can start to be a little bit more efficient about it, because if we know it's uppercase because it's a currency, we can say, okay, there are only 26 letters in the alphabet. So it's 26 to the power of 3 is the maximum number that we would ever need to store, and therefore we could store within that number of digits every single uppercase alternative of letters. However, if we go a little bit more intelligent still, and again, you need to understand your data, and this is where it's really important to understand your data, because it's a currency. There are only 163 currencies defined by ISO. There's only so many currencies. That means that we could store them in 1 byte. And even if you want to be flexible, you could create yourself an escape code that says if it starts with 0, then the next one is actually the 3 digits, or the 3. So I want to use, for example, XAU for gold, or XPT for platinum, or X something or other for some new cryptocurrency. We could still do that, so we still have the flexibility, but we get a lot more efficiency out of it. So if we now move this into binary, and we find a way of storing each of these. Now, I went through one of these. I believe this is a laser, so let's give it a go. Oh yeah, here we go. Notice I'm being very safety conscious here. I normally have really decent lasers that cut holes in things, so this should do. So we've got a date, and we've already realized we can actually make the date down to two bits very, very easily. We've got a by cell. How many bits do you think I need to store by cell? 1, exactly. Now, it might be inefficient to store it as 1 bit, but we can come back to that. We could just store it at least as a byte. It's either -1 or 0. Currencies, we could come up with an algorithm on this. We could say the maximum number of decimal places. We could work out something. If they always have lots of zeros in it, then we can do something times 10 to the power of whatever. And it's the way doubles are typically stored. So again, we can be relatively efficient, but probably not massively more efficient than the IEEE standard. So probably 4 bytes in that. We're back to exchange rates. Currencies here, we can now put those in 1 byte, another number, and another date. So we can now compact this down. And what we get, this is just a comparison. So we go to our code. Now, if we do this, the whole beauty of an object-oriented language is if someone writes the implementation, as long as you're using the getters and setters, you don't care what sits behind it. So if we take your standard get trade date, as it returns the trade date or it assigns it, which is the standard getters and setters, but we put the implementation for the binary stuff underneath it, all I'm doing here is I'm finding out the offset. So this is just some word from byte, what does it say? Word from bytes from offset 8. So I've calculated where the offset is. I'm just getting a word out of that, so it's basically returning a long, but it's only 2 bytes of it is significant. I'm now multiplying it by the 86,400,000. The reason that it's got 3 extra zeros on the end is quite simply because it's measured in milliseconds. And I can now return the date. And it returns it as a classic Java date object, meaning all the code that I use to do the comparisons is still working with the date. So everything's still working as it should do. Other thing, interestingly, is, OK, I've got a new, so you could argue, hang on, I'm creating another object. There's an object being created, and I really want to avoid creating objects. This is created on the Eden space, so it's garbage collected really quickly. So if I'm actually doing comparisons, I get the date back, do the comparison. The comparison is either true or false, and it's garbage collected immediately. So it doesn't go into the long-term space. Same with the set, exactly the same. Take the trade date, put it into a long, classic Java long, divide it by the number of milliseconds in a day, and then just do a little bit of stuff that used to be everyday stuff in C, C++, which sadly most Java programmers have forgotten these days, but that just basically pushes the little bit of a rotate in there. So because of the time, I've got code. We'll carry on with the slides. Basically, it's just going through the code on this, as you probably saw as I was preparing. We'll come back to that. All it does effectively is creates a million objects in using that classic object that I showed you, and it creates a million objects using the binary compaction of which the code is all there. So if anybody wants to, if you have a memory stick, you can walk away with the code. It's just a nice, simple demo. Give you some of the results of that. So with the classic Java version, it takes, as we said before, 328 bytes. The binary version takes 39 bytes. Now that's not doing anything overly clever, and we get an improvement in memory, certainly. The serialization, now the way Java serializes is that it's basically writes out the name of the class, so it's a tag value pair if you like, it writes the name of the class. So if all of your classes have massive package names, your serialization will be larger. So one of the secrets of already optimizing serialization is to have your packets named A.B.C, etc., which is one of these things that obfuscation does for you as well. So the serialization is pretty large, but it also then contains this in there as well. So there's a lot of it, and not only that, but it serializes the class name, and then it says java.lang.string, java.util.date, java.lang.string, etc. So those are all hidden in here. So every single row now is now almost 10 times the size that it was originally. Serialization for this, classic serialization is exactly the same because it still writes the name of the class and then writes the data. So we've got this overhead of about 40 bytes, which is the name of the class that I created. If we do custom serialization, there's a unique thing about this binary is because we know exactly where the data is, if you're using classic Java, you don't know where your objects are. You have a reference to an object, but the memory that's used by that object could be anywhere in memory. Now you can take the data out of it, so you can create a copy of it, but the whole point of this is that when you write it to disk or to the network, you've got to write each of those individual classes, hence the size of this. If we're doing a binary version, we know exactly where our data is because we have an array of bytes. So rather than store 39 bytes, typically experience will tell us to round it up to the nearest 8 because that's just the way things work these days. We round it up to 40 bytes. It means we can store every single row in 40 bytes. The interesting thing is now that when I read that 40 bytes back, it's in exactly the same format as when I wrote it out. So when I read it back, it's in a format that the CPU can read, and it's in a format that the CPU can now compare. So it can compare dates because it's in the binary format. It can compare the strings because they're either the same because they're just bytes, and the same with the numbers. So reading this back, deserializing it, not only do you need to deserialize something which is 16 times larger in this very small example, so we need to read 16 times more data off the network, we also need to decode that 668 bytes as well. Whereas this, we read it off the network, we put it straight into memory, and it's all ready to use. So there's no processing to be done on this. So when we look at the time to serialize, we go from 41 microseconds. This is for just doing a million of them, so you put 10 million. It comes to roughly the same sort of number. Again, this is just for this example. But when we look at the custom serialization, so we're writing out large arrays of this, we can go from 41 microseconds down to 44 nanoseconds. That's a 1,000 times, roughly, performance increase. And this is the sort of performance that we're actually seeing in practice. So it's the sort of numbers we're getting out for doing really, really small changes to your data. Quick look at this and comparing it. I'll enlarge these. So this is the, so again, putting the post-mortem garbage collection analyzer on from the JClarity. This is using classic Java objects. This is using the binary. Now, you can't see this, but that 10 seconds there is exactly the same as that 10 seconds. Let me use the laser. That one there is the same as that one. That is 200 odd seconds. This is 40 or so. So I'll enlarge that. So that bit takes the same amount of time. That's the serialization, and that's the deserialization. It takes just 40 seconds as opposed to 200 seconds. So it's exactly the same. Also, let me flip back. That's 8 gigabytes of heap. That's 2 gigabytes of heap. And I sort of scaled them to be roughly the same size. So we're doing exactly the same amount of work, using exactly the same piece of code. That's what the demo I was going to show you, with 1/4 of the memory and 1/5 of the speed. And that's what we get out of that. More importantly, the garbage collection times, when we look at the sort of full GC pause times, there are actually 2 glitches up here which are half a second each. And this is why what happens is we've got too much garbage and it has to go into a full sweep, where it has to lock down the JVM to stop anything else creating any objects and go through it. So we have 2 half-second pauses here. Now again, to give you an idea of the scale on this, remember this is 200 seconds, this is 40 seconds. This rung here, so the first line here, is actually higher than the top of this graph. So this is half a second. And so if we enlarge that one very slightly, that's 45 milliseconds. So this, again, for the data analytics that you're doing, remember this is the same sort of thing if we're now distributing this architecture. This is the sort of performance you can get by distributing your work from one machine to another machine. It makes this very, very significant difference as we scale out. As we're sort of taking that cliff, we're reducing that cliff into just a small ledge. It makes a massive difference. So in the serialization and deserialization, naturally when we were sort of talking to other clients and prospects and people about this, putting it into production, which we have done now, naturally they come up and say, oh, what about Avro, Cryo, Thrift, Protobuf and things? We're using all of these things. Now, yes, they are faster than Java serialization, but I've just demonstrated, or at least shown you, that Java serialization is about 100 times slower than it needs to be. So there's a huge amount of room for scope for improving it. All of these things work beautifully well, but what they do is the same. It's tag value pairs. I'm going to send you a string, here's the string. I'm going to send you a date, here's the date. They do it more efficiently than the way Java does it, so there's a massive performance increase. But when you send data from machine A to machine B, you typically know what you're sending. So machine B knows what machine A is going to send it. So why send all the information each time? Why send, I'm going to send you a string, I'm going to send you a date, I'm going to send you another string. If you know that, string, date, string, this one knows string, date, string, just send the data. It's like the difference between XML and a common delimited file. So all of these things give you a huge amount of flexibility, but they still work in a tag value pair. If you're sending data from A to B, you know the contract. Don't bother to send the contract every time you send the data. Send it once, you've got a class on one side, class on the other side. The class that's sending should send exactly the same information to the class that's receiving because they're the same classes. So you've got your customized serialization on each one. So to give you a comparison on these, this is using the JMH. Anyone use JMH here? Java Micro Benchmark Harness. I seriously recommend you take a look at this. If there's anything you write down and walk away with externally on this, it's this Micro Benchmark Harness. It's really, really powerful for doing, as the name would suggest, micro benchmarks. It gives you all of this data beautifully simply. It needs Maven, which I hate, to get it running. Because it actually does code modification. Someone's mother's calling. But it gives you all of this data. So using the binary benchmark, we're getting on this sort of an average of 171. This is deserialization and serialization, 170 nanoseconds. Whereas the Cryo benchmark for the same thing, we're up at the sort of high 300 to 400 nanoseconds. And again, the more complex this is, the better the gain we get over these technologies. And you can see these sort of error marks that you get. This is the micro benchmark harness is superb. There's the, if you want to take a picture of that or ask me afterwards. There is a thing online that tests all of these. And for years and years, I've been ignoring it until one of our clients said, hang on, we've tested you against this. And this is actually a client's graph, my ex-company's client now. So these are, you can see Protobuf, Cryo, proto stuff, wobbly, all these various different things here in terms of this is the serialization and deserialization that it takes to do these. Now, this isn't the comma delimited file that I showed you before. This is the one that's on the open source test. And this gives you some idea of the sort of performance benchmarks we get out of this. So it is very, very, very fast. So coming back to the analytics, when you're comparing your data, one of the things which I hopefully showed you before is that we're not changing the interface. So we still got the getters and setters in there. There's no change. So you can just slot this in without changing your code. And so as I've now been a fan of the lambdas since they came out in the beta, I can now still do map reduce, etc., using exactly the same get currency amounts, group them by currency. So we've got get currency here. Now, currency is just stored as a single byte, but it still returns GBP, JPY, EUR, etc. It's just storing as a single byte. So all of this works just as well. And I can now process through 1 million very, very complex messages. I mean, these are horribly complex in just a tenth of a second using this sort of thing, data. What I was saying before is if we can improve the way we've got things, we don't actually need to go into serialization. And if we don't need to scale out, what we've done is we've actually got 10 to 50 times more data into one machine. We don't actually need to scale out. But when we do scale out, we have a lot more flexibility to do that. So we should, a few more minutes left. So very briefly, we can move this into Spark. Now, Spark is the far more modern, vastly more sensible version of the MapReduce over Hadoop. Hadoop was just a bunch of nutcases that got together and decided that they couldn't figure out these non-SQL things, so they decided, right, take all your data out of the non-SQL and stick it into yet another relational database. And all the stuff that we go through the object relational mapping, basically take it all out, stick it into a relational database, and then we'll search through it for you. So there's an awful lot of work to extract the data, and it's an awful lot of work to do the processing. Spark is a vastly more sensible way of doing that. One of the problems with Spark is, however, as soon as you exceed the capacity of your machine, you've got two options. One is you start using disk, because disk is cheap. Next one is that you hit the network and you distribute the tasks that you've got. If you distribute, we hit the serialization problem, and serialization is worse than, or as bad as hitting disk. If we hit disk, it's the same. We've got to store the data. So this red mark is basically what it takes in a single machine. This is what it takes when we hit the disk. When we use binary serialization, as I said, we take this cliff that we've got and we turn it into a little ledge. And so we see the difference between running in the same machine and running on a distributed machine. What this means is that we can take Spark and we can now run it across multiple machines using binary serialization with virtually no impact at all. So that basically means we can do a map reduce on a very, very large network. Just enlarge that very slightly. Again, just to explain, we've got cached disk or serialized memory, and this is basically running in memory. So that's the default. If it runs in memory, it's beautifully fast, really nice and efficient. As soon as we come out of these, we hit these nasty walls here. Cryo improves it slightly, but when you use binary, we get a massive performance increase. So to really sort of sum these up, if we're using this sort of technique, once you get into the swing of it, you can create a class for strings, you can create a class for dates, you can create these different mechanisms. We used a code generator to do this because it was much, obviously, once you do it once, you can regenerate multiple times. So it creates something really small, so we don't need to scale quite so much, which is a big advantage. It's extremely fast. Coming back to that, you remember we were talking about caches right on the second slide on this? You'll notice the objects take 22 milliseconds. The binary takes 17 milliseconds. Now, we've got extra work to do in the binary because we've got to unpack it effectively. Well, not unpack it, but decode it in some cases. It's actually faster because your data is now in a single byte array. It can actually go into the L3 and the L2 cache. So we're not going into memory. So if you read in 10,000 of these things, it may be only 16 megabytes, it can go straight into the cache. So the CPU is now fetching out of its cache, not into memory. So again, massive performance optimization. And finally, transport friendly. Again, we see this, naturally there is a slight decrease on running it out of memory, but putting it across the transport, we've got a very little, very, very small overhead on top of that compared with the multiple seconds that it takes using standard serialization. It definitely does work. It is something which you could go back today, and within a day you could start, if you're using the Java micro-benchmark harness JMH, you could start to optimize these. You could start to see results out of this within the hour. It's look at the objects you've got, look at the serialization, look at what you're reading and writing from disk into memory. You can see this return really, really quickly. We took this to the extreme because we created a product out of it, because we did financial services messaging, and the company Gresham has now got that to do financial services messaging and analytics as they do for their clients now. We spent a lot longer on it, but you can, and I've done this with sat and pair program with people for half a day. You get massive gains out of this, so it is something you can do. I think we've pretty much finished on the dot. Thank you.